Yeah. So let's calculations. So if any power system network is given and fault is unbalanced fault, how to calculate the currents that are going to there, the fault currents is what is today's objective. So far what we have learnt will be useful in today's class. So before we move forward, let me quickly go through lecture 25. I just want to review it. So just give me a minute. I'll open the lecture 25 notes. And in the previous lecture, we talked about symmetrical components and sequence networks. So this was 28th Feb. So obtain, we started right away with the example problem, obtain symmetrical components of following unbalanced currents. So IA, IB, IC, three currents are given. As you notice, they are not symmetrical. So why IA, IB, IC are not symmetrical? Because first the magnitude is different, 1.6, 1.0 and 0.8. So for a balanced system, all magnitudes should be same. And here the difference is only 60 degrees and so on. So they are not balanced set of IA, IB, IC. But IA, IB, IC I want to express in terms of sequence components and also draw the phasor diagram. So and you know this A matrix where A is one angle 120 degrees. So given this A matrix, so the ABC can be expressed as A into IA0, IA1 and IA2. So IA0 is the zero sequence component, IA1 is the positive sequence component, IA2 is the negative sequence component. So since this is known and this is known, unknown is this side, so I just multiply with A inverse on both sides. So I'll get IA0, IA1, IA2 is A inverse of IABC. And by simple calculation in MATLAB, IABC, I got these values of IA0, IA1 and IA2. So now how to verify? So zero sequence component is 0.5 at 90 degrees. So I draw that vector here. So this is 0.5 at 90 degrees. And then the positive sequence component is like this, IA1. I think it is 0.9 with minus 1.4 degrees. And then finally the third component is IA2. So if I add these three, I get the total IA, which is nothing but 1.6 at angle 30 degrees. Of course, this drawing is not as per the scale, but if you draw the drawing with exact scale, you will notice that mathematically it will be matching. So what do you say? A phase current is nothing but zero sequence plus positive sequence plus negative sequence. Same thing applies for B phase current also. So you see B phase current is this one, and then IB0, IB1 and IB2. Similarly, I asked you to verify for C phase current. I hope you had done that verification. So again we have a reverse problem, another example where the sequence voltages are given and you have been asked to find the actual phase voltages VA, VB, VC. So this is again straightforward. Just given the sequence voltage, just multiply with A matrix and you will get the answer. So code you can refer. I have left it at the end. So these are VA, VB, VC. So now coming to complex power. So we know that power is VA into IA star plus VB into IB star plus VC into IC star. This is the power in the three phase. So that I can represent it as VABC transpose and IABC star. Then calculation we got 3 times that of the sequence components. So then I went for representation of three phase load star connected, and then this we have done if there is a load, how it appears in the sequence components. So I calculated sequence component impedances of the load. So and then finally I got ZS plus 3ZN, ZS and ZS. So this is about the load. So this is what we have done. So not only that, we have also made one calculation. So one star system is there, and I am introducing some kind of a unbalance in it because the voltages themselves are not balanced. So this looks like a star connected source with star connected load. Load is balanced, but the source is not balanced. So source voltages are different. So then what I did is we had calculated the sequence components. So voltage sequence components I know. So from that currents I calculated, and finally we get the actual currents IA, IB, and IC. So these currents have been marked in the circuit. We also done the verification of power. So finally 705 watts of power and 2115 watts of power have been consumed by the network. If I use this formula, that is the components for A phase, B phase and C phase formula, I am getting this power, and if I use the components formula also I am getting the same power. So therefore we verified that the powers are matching. So this is what we have done in the last class. So for your convenience, I have also copy pasted all the codes. So this is the first program and this is the output of the first program. This is the second program and this is the output of the second program. And this is the third program and this is the output of the third program. So I strongly encourage you, those who have not already done, please go through the link homepage of this course, download the notes, try to run the MATLAB code and then try to get the solutions. I've been saying, refer to any power system textbook, practice more and more problems, you will get more knowledge and more idea and grip about this. So this was about the last class. So any doubts you have up till last class? I'll give you a couple of minutes. You can think about any, if you have any doubts, you can ask. Today we are going to see sequence networks. So let's say our three-phase network. Then for that three-phase network, I'll look at the sequence network. And then finally, example problem. So the first three-phase network is basically star-connected load. So you know how the star-connected load looks like. So what is the sequence network of it? And then based on that, one example problem. Next one is generator. So three-phase generator, you know. So how does it look like in sequence network, and an example problem based on that. So then generator plus LG fault. Let me write it. Generator with LG fault. So this is our three-phase network. For that, what is the sequence network, and a problem based on that. Next one we'll see generator with LL fault. So what is the sequence network of it, and what is the example problem on it. Next one we'll see generator with LLG fault. Again, what is the sequence network of it, and what is the fault calculations example problem. So this is the plan for today's lecture. So let me just make it as a table. This is 1, 2, 3. So all these cases we are going to discuss today. So now for given a three-phase network, what is a sequence network? We need to calculate. So three-phase network, sequence network will have Z012. The impedance expressed as a zero sequence component, positive sequence and negative sequence component. So there is some kind of derivation involved. Already the first case we have done in lecture number 25. Previous lecture we already done this. So lecture 25 we already done this. And we also done the example problem in lecture 25. So if you refer to lecture 25, this is what we have done. So, but still I will review. So, star connected load. So what is a three-phase network? Three-phase network will be like this. It may have an impedance connected to the ground. So this is Zn, this is the neutral point, this is the A point, this is the B point, and this is the C point. And this is Zs, Zs, Zs. So for simplicity, I am not assuming any mutual impedance between them. So this one, if I convert to sequence components, what do we get? So if I convert this network into sequence components networks, so already we had seen in the previous lecture, that is Z0, or let me write it below. Z0 will be Zs plus 3Zn. This is a zero sequence component of current. Z1 positive sequence impedance will be nothing but Zs, and Z2 negative sequence impedance will be nothing but Zs. So given these equations, I can draw the circuit. So what is the circuit? So the circuit is like this. This is Zs plus 3Zn. These two are in series, and whatever comes out of it is VA0, and then IA0 will be going in. This is zero sequence network. What is a positive sequence network? Positive sequence network will be, that's it. So this is VA1, and the current it takes is IA1, and then the impedance is Z1. Nothing but Zs. So this is positive sequence network. The negative also exactly same, VA, and this is Zs, and this one is, sorry, this is VA2, and this is IA2. So if this load is given, Zs and Zn values are given, so what you have to do is the VA0, VA and VA2 of the voltage. Then from this circuit find out what is IA0, from this circuit find out what is IA1, from this circuit find out what is IA2. Once you get IA0, IA1 and IA2, you can find out IA, IB, IC easily by multiplying with matrix A. So this is about the first case, star connected load. This derivation we have seen in lecture 25 already. So if you have any doubt here, please refer to lecture 25, how to represent a three-phase load in the form of a sequence network. So this one circuit becomes three circuits. Okay. Now let's talk about the second case, that is generator. So what is a three-phase network? So three-phase network is something like this for a generator. There is a EMF and then there is a impedance. There is another EMF and there is some another impedance. There is another EMF and then another impedance. And the neutral point is connected to ground. So this neutral point impedance is Zn. This is Z source or Zs. This is EMF induced in A phase, C phase. So minus plus, minus plus. And finally, this is line current IA, this is line current IB, this is line current IC. And these points we are calling it as A, B and C. So this is a three-phase network of a generator. If I am interested in finding out, let me also mark the neutral current. This one is IN, neutral current. Now, what is VA, VB and VC with reference to the ground? So, this is the ground and what is VA? So, if I want to write down what is VA, so I can write here easily. So, maybe I'll write it here VA, VB, VC. So, what is VA? So, look at this. So, at 0, the drop here is IN into ZN, then EA is increasing, and then again there is another drop. So simply I can write EA minus INZN minus IAZS. So this is nothing but the A phase voltage. So A phase voltage is this voltage drop plus this voltage drop. So out of total EMF induced, 2 voltage drops I am subtracting. So it's simple Ohm's law I have written for VA. What about VB? So the voltage at this point is nothing but from here 0, voltage drop here, and then EB is there, voltage is increasing, and then finally this one. Just a minute, let me check this once. I am concerned about the direct IN into Zn minus IC into Zs. So this is just Kirchhoff's current law for each of this. So let me move this circuit down. Now we know that IN is nothing but IA plus IB plus IC. Because you just simply apply Kirchhoff's current law here, incoming current is IN, all the other currents are there. So I'll get like this. So if I substitute this here, then I'll get finally something like this. VA, VB, VC is equal to EA, EB, EC minus ZS plus Zn, ZS, ZS. Sorry, Zn, Zn. Similarly here Zn, Zs plus Zn, Zn, and Zn, Zn, Zs plus Zn. So into IA, IB, IC. So the same equation, I am just substituting this and then I am able to write it in this form. So if you actually expand each of this, you will find it is exactly the same. So it's not that difficult. So I am showing you this short derivation so that you get an idea of how to derive the sequence components networks. Now I will use some short notation. So let's denote it as VABC equal to EABC minus ZABC into IABC. Just short form notation. Now these sequence components I can introduce. So VABC is nothing but A into V012. EABC is nothing but A into E012. And then ZABC will remain like this. IABC is nothing but A into IABC. So again, just converting to sequence components. Converting to sequence components. So after doing that, what do we get? Now multiply A inverse on both sides. So A inverse into A, you will get V012. A inverse into this, you will get E012 minus A inverse ZABC A into I012. Sorry, this is 012. in the previous. Okay, so now this matrix you focus, this is A inverse into ZABC into A. So this one, let me denote it as E012 minus Z012 into I012. So this I can just denote it as this one. So it turns out that if you calculate what is Z012, because you know, see A is known, ZABC is known and A is also known. So if you from all this you calculate Z012, you will get like this. Z012 will be nothing but ZS plus 3ZN, ZS, ZS. That's all. So the rest are all zeros. So this is the Z012 matrix. Similarly, E012 you will get, because EA, EB, EC are there, but only positive sequence is there. So zero sequence you will get 0, and then this you will get EA and this you will get 0. So this is E012. So finally, if I substitute this here and if I substitute this here, finally I will get V0, V1, V2. So these voltages I will get minus Z0, IA0. You will get EA minus Z0, Z1, IA1. So this is VA0, VA1, VA2. You will get minus Z2, IA2. So again, this is just simple substitution. So these are the important equations for your sequence components of a generator. Now instead of writing like this, I want to write it as a three different networks. So just notice what I will do. So look at the first one. There is a voltage source and there is a voltage drop. So I represent a voltage source. This is a voltage source E A. Then there is a drop. And then finally, the voltage outside is VA1, and then this is plus, this is minus. And what should be the current direction? Current direction should be outwards. This will be IA1. So this is nothing but this equation. So if you write equation for this, what is VA1? VA1 is nothing but EA minus IA1 Z1. So this network is giving this equation. Now what is the network for this equation? VA2. So VA2, the network will be like this. Just one impedance is there. The impedance is Z2 and the current direction is IA2. This is plus, this is minus, VA2. So what is VA2? VA2 is nothing but Z2 into IA2. So similarly, you have the zero sequence. So this is the, now what is the network of the zero sequence? So the network of zero sequence is like this. This is Z0 and this is IA0. So this is positive sequence network, this is negative sequence network, and this is zero sequence network. So this, so what we have done is I started with three phase generator. From the generator, I have written Ohm's law equations, voltage equations, and then I manipulated and then I converted to sequence components. And from so basically this is equal to Z1. Sorry, this is equal to Z0. This is equal to Z1, and this is equal to Z2. From the three equations, I got the three circuits. Okay, so these are the sequence networks of the generator. Actually, these are very important. Once you have this, then all other fault calculations will become very easy. So intuitively what you understand is the A phase voltage generation, the positive sequence voltage generation will only come in the positive sequence network. We are not generating any negative sequence voltage. We are not generating any zero sequence voltage. VS0. Now, once I have this, let's go to the other cases. So, what are the cases? So I have done this now. Example problem we'll do it later. First, I'll complete this column, then we'll do the example problem. So, generator with LG fault. Line to ground fault. This is line to ground. So, the same network you will be considering, that is, you have a generator impedance, then this is connected through Zn, this is EA, EB, EC. This is VA, VB, VC. So all this to this zero node. So if I mark the currents, this current is IN, this current is IA, this current is IB, and this current is IC. Now there is a line to ground fault. So that is what we have to investigate now. So let me give the. So line to ground fault means there is a fault, there is a ground here, there is a fault impedance Z fault. Through that fault, this line is connected. So under such scenario, what will happen is what we are trying to understand. So since the derivation is quite long, so what I suggest is for derivation, refer to Hadi Sadat textbook on power system analysis, and you can refer to section 10.5. So what I am writing is directly the sequence networks. So this is the three-phase network. What is a sequence network? Okay, so sequence network, first I'll draw the individual sequence network for the generator without any fault. Already we have done it in the previous segment. So I'll just, same thing I'll reproduce here. So what is the sequence network of a generator? So first we have EA, then there is Z1. This current is called IA1 and this voltage is called VA1. This is the positive sequence network of a generator. Then what is the negative sequence network of a generator? So negative sequence network of a generator is like this. This voltage is VA2 and this is Z2 and this one is IA2. This is a negative sequence network of a generator. What is the zero sequence network of a generator? This is the zero sequence. Z neutral and this is I0, IA0 and this is the zero sequence network of a generator. In fact, this one I'll keep repeatedly using, so I'll just make a copy of this. So copy. Okay, so I have made a copy of it, later on I'll use it. So now let's talk about the LG fault. So if there is a line to ground fault, what you have to do is connect all the three networks in series along with the fault impedance. So how to connect all the three networks in series? So you already know. So how to connect these two in series? So this point you bring it here. So this is connected in series. Then this point you bring it here. And finally this point you bring it outside and this point you bring it outside. So these two you just connect 3 times Z fault, whatever the impedance of the fault. Then your analysis is completed. So this diagram now is sequence network of LG fault. So what happens is, you know the voltage. So you can find out what is VA1, VA2, VA0, or in fact you know what is EA. The EA is the EMF induced at the beginning of the fault. So EA is known, Z1 is known, Z2 is known, Zn is known. So from this, ZF is also known. From this you find out the current. And once you find out the current, then you can find out the fault current. That's what is the objective. So how to use this network? So can you tell what is current now from this? So you see IA1 is equal to IA2. IA2 is equal to IA0 because all three are in series. So all three currents are equal and the total current will be, you see what is the total voltage in this? Only one voltage source is there, EA. So total voltage is EA. And what is the total impedance? Total impedance is Z1 plus Z2 plus Zn plus 3ZF. Z1 plus Z2 plus Zn plus 3ZF. So if you do this, then the current will be nothing but IA0 or IA1 or IA2. And once you have this, you can find what is IA, IB and IC. So this is the analysis of LG fault. So again, what I have done is I have taken a generator, created LG fault, but the derivation of that refer to section 10.5 in this one, you will be easily able to follow. Final output is this circuit. And finally, this is the formula to calculate IA0. Okay, so let's continue. This diagram, let me move it. Next, what we are going to study is line to line fault. So remember, first I am giving all the formulas. In the end, I will solve one example problem that will make it everything very clear. Okay, so third case, generator with line to line fault. So again, how does it look like? So there is a generator, there is another phase of the generator, another phase of the generator. Then there is a neutral Zn. So this is Z1, sorry, this is ZS, ZS and ZS, EA, EB, EC. In fact, I should have copied the previous diagram. In fact, I'll do that. Sorry for the disturbance. I'll just delete this. Just copy this. So I have a generator. Now I want to create a line to line fault. So how to create a line to line fault? So take this line and fault impedance is Z fault and short circuit with the other line. So two lines are short circuited. So this is line to line fault. So this voltage is VA, this voltage is VB, VC. So you notice VB and VC will be almost equal except small voltage drop in this line. So for this, what is the derivation? So again, derivation of sequence networks. So again, since the derivation is quite long, I am not giving you the full derivation. I would say refer to section 10.6 of Hadisada, Power System Analysis textbook. So what you find from all of that is the sequence networks. So So what are the sequence networks is like this. Whenever there is a line to line fault, the ground is not involved because there is no G. Ground is not involved, and whenever ground network will not play any role. So this is simply disconnected. Now what is connected is this. So this line is connected to this, and this line is connected to this. That's all. In between there is a fault impedance, Z fault. This is the line to line circuit. So from this you notice one thing. What is IA? IA1 is exactly opposite to IA2. So the positive sequence current will be exactly opposite of negative sequence current. And IA0 will be 0. So this is line to line fault. So what is the formula? So if I want to find IA1 in this, what I will do? What is IA1? IA1 is nothing but total voltage is EA. So EA is in the numerator. Total impedance Z1 series with Z2 series with ZF. That's all. So Z1 plus Z2 plus ZF. So if I do like this, I will get what is IA1 and what is IA2? Nothing but opposite of, that is minus of IA2. So once I know IA1, IA2, IA0 is 0, I can find out the IA, IB, IC easily. So that is this. We'll see an example problem based on this. So just to orient you, going back to our overall table, so generator with LG fault, I just discussed. Now finally, what is the circuit for generator with LLG fault? This is what we are going to see now. So let me go back to my current page. So I'll draw a line. Generator with LLG fault. So what I want to do is again I copy my generator. So this is my generator. So on this generator, I want to create a LLG fault. So two lines I'll short circuit straight away. So two lines are short circuited. Then there is a Z fault. And finally this is connected to the ground. So the current that is going into this is the fault current IF. So IB and IC is equal, IB plus IC equal to IF. And that fault current is anyway going through the ground back to the neutral of the generator. So this is the circuit. So for this, what are the sequence networks? So again, I request derivation of sequence networks. So refer sequence network for LLG fault. Refer to section 10.7. Okay, so of Hadi Sadat and understood. So what are the sequence networks? The sequence networks are like this. So this is the generator sequence network without any fault. Now there is a line to line to ground fault. Then what you have to do is first the negative sequence and this one you connect in parallel. Parallel connection between these two. So what you have to do is this is 3 times the fault impedance connected to this and this one connected to this. Then these 2 points you connect to this. So this is a circuit that you have to solve for analyzing a line to ground fault. So this is sequence network for line to ground fault. Now I can ask a question, what is IA1? How to find IA1 in this? So you notice that there is a parallel branch here. So let's simplify the circuit. So see this branch Zn and 3Zf are in series. Okay, so that's I'll do that. Zn and is also impedance 3Zf. These two are in series in the right side branch. This branch only Z2 is there. So only Z2. So these two are in parallel. You notice these two are in parallel in this diagram. Then here I have one EMF and one impedance. So this is Z1 and then one EMF. EA. So this current is IA1 and this current is IA2 and this current is IA0. Now given these values, can you find IA1, IA2, IA0? Of course you can find, it is very easy. So for the parallel branch, what is it? So Z2 is in parallel with Zn plus 3Zf. So what is this overall impedance? The two impedances are in parallel. That means Z2 Zn plus 3Z2 Zf divided by Z2 plus Zn plus 3Zf. Just looking at the parallel circuit. So this is the overall this thing. Now, what is the overall impedance? So Z total impedance equal to. So Z1 in series with the parallel combination. So this is Z1 plus this. And once I know total impedance, what is the current? IA1. IA1 is nothing but EA divided by Z total. So once I get IA1, then you calculate what is IA2. Then you calculate what is IA0. And you get IA1, IA2, IA0. Three sequence components you know. Then you can just multiply with A and you will get the IA, IB, IC. Phase currents you will get it. So that is the procedure for this case. So this is the circuit and this is the simplified circuit. It's very easy. You can do that. So I think we completed all the cases. So let me go back and refer to my first page. Completed all the cases. So I have given you sequence network of simple load. I have given you sequence network of a generator. I have given you sequence network of generator with LG fault. I have given you sequence network of generator with LL fault. And finally sequence network of generator with LLG fault. So all cases we have discussed. Now let's do a problem. By doing this problem, you will understand much more. And as I said, already this problem was done in lecture 25. So refer to lecture 25, we already done how to solve a problem with star connected load. So let's do other 4 problems. But before I jump to the problem, let me wait for a couple of minutes. If you have any doubts, please feel free to ask your doubts based on what we discussed so far. And if you have any doubt problem, which I actually looked at the textbook and created myself, so we will solve that problem, and through that solving that problem, we will try to learn how to do the fault calculations. So I'll explain the problem. Example on unbalanced fault. So consider the following power system. Where S base is 100 MVA and V base is 20 kV for generator. So I'll draw a small power system network now. So there is a generator and star connected and the neutral is grounded. So Zn is 0.04 per unit. So the neutral impedance is 0.04 per unit. So what is the base? S base is 100 and V base is 20. Now the impedance of the generator itself is J 0.08 per unit. Then this generator is connected to a bus bar and there is a transformer. So the voltage is stepped up here. So the transformer rating is 20 kV by 120 kV. So the voltage is stepped up here. And the impedance is J0.04 per unit. So this is the impedance of the transformer in per unit. So again, the voltage base is 20 kV, 100 MVA. Now, because we are going to the high voltage side, on this side the voltage base will be 120 kV, but S base will be 100 kV. So there is a line again, so transmission line, and there is another bus bar. So if I number the bus bars, then this is bus number 1, bus number 2, and this is bus number 3. Now what is the impedance of the line? So the impedance of the line is J0.1 per unit. So the fault is occurring at bus 3. So, and this is the fault. And the fault impedance is, Z fault is J0.1 per unit. Now what type of fault I have not yet specified. This is the power system with 3 buses, 1 generator, 1 transformer and 1 transmission line. Then at bus 3 there is a fault and the type of the fault I have not given. So the question is, calculate fault currents. That is IA, IB, IC. 3-phase fault currents for, so I consider different cases. So case 1 is balanced 3-phase fault. That is LLL fault. Case 2. All the things that we have done. So this is unbalanced fault. That is line to ground fault. At bus 3. Case 3. Line to line fault at bus 3. Case 4. Line to ground fault at bus 3. So 4 different faults I am considering. Each case, what is the fault current? What is IA, IB, IC? I want to calculate. So have a look at the problem. Try to spend a couple of minutes understanding what is the problem, and then I'll solve it. So just take 2 minutes. The question is on your board. So just look at the question and try to calculate the fault current. So I'll write here S base is 100 MVA for generator. Look at the question, look at the diagram, what is happening, and one by one I'll solve this. Any doubts about the question? By the way, EMF generated is 1 per unit. EMF generated is 1 per unit, there is an assumption, and so far there is a system is on no load. So there is just a fault here. So how to solve this? So the first step is you represent the network as a reactance diagram. So how to represent the network as reactance diagram? So the neutral also has some impedance, remember that. but we'll come back to it. First, look at the reactance. So this is the answer. Step 1, construct the reactance network, reactance diagram. So if you remember, there is a EMF, then there is a impedance of the EMF, then there is a transformer, then there is a transmission line, and then we have the line. So what is the impedance of, so this is EG is 1 per unit. What is the impedance of the generator? I have given it is J 0.08 per unit. Since everything is already in per unit, I can add them in series. Impedance of the transformer 0.4 per unit. Impedance of the line 0.1 per unit. So what is up to this bus 3? What is the total impedance up to bus 3? So 0.08 plus 0.04 plus 0.1. So 1.4.22. So finally I will get the EMF induced and then J 0.22 as the impedance. So neutral also has the impedance. So I'll just write Zn is 0.04. Okay. So once I have this, so if there is a three-phase fault, what is the fault current? In fact, I can directly take case 1. What is case 1? Three-phase balanced line to line to line fault at bus 3. So we don't have, because it is balanced, we don't have to use any sequence components. So here if there is a fault and fault impedance is also given. So, but then this is line to line to line fault. It's not a line to line to line to ground fault. So I will not consider the fault impedance. I will just directly take that fault impedance is 0. So fault current will be nothing but Eg by Zs. Or let's call it as Z33, the equivalent impedance of bus 3. So that is this one. So 1 divided by J 0.22. So how much is this? So let me take out my calculator. 455 per unit. So this is a fault current. So how to get the actual fault current? This is in per unit. How to get it in amperes? So see, S base is 100 MVA divided by V base is nothing but V base is 20 MVA for the transformer. So, sorry, 20 kV for the generator. So this will be 5 times. K will go with mega into 10 power 3 and voltage will cancel. So I base is 5000 amperes. So if base current is 5000 ampere, then what is the fault current? I fault will be 5000 into minus J 4.5455. So let me do that. $22,727 amperes. Huge current. This much fault current is flowing for a three-phase fault, balanced fault. So very huge current. So that was case 1. Now let's do case 2. So what is case 2? Case 2 is this, line to ground fault at bus 3. Okay, so LG fault at bus 3. Now what I want to do is I will go back to my previous notes and then I will copy the case for LG fault. So I think you had written down some notes. So just I am copying that circuit and then I'll paste that circuit here. Now I have all the values. Let me put the values. What is the value of EG? Value of EG is 1.0 per unit. What is the value of Z1? Z1 is a positive sequence impedance. We calculated that is J 0.22. Now, what is the value of Z2? Negative sequence impedance, that is also J 0.22. Positive sequence and negative sequence both are equal, as per the derivation which we saw already. And what is the, I think this is Z0. What is Z0? So Z0 is nothing but Z1 plus 3Zn. Sorry, Zs plus 3Zn. So what is Zs? Zs is 0.22 plus 3 into point, so J 0.22 plus 3 into J 0.04, the neutral impedance. So finally this value will be, this is 0.12 and 0.222. So this will become 0.32, 0.34. So this is the third impedance. Now what is the Z fault? Z fault we already know, given in the question, 0.1. So finally this will be 3 into J 0.1. So that is nothing but J 0.3. So from this entire thing, can I calculate what is the current IA1 or IA2 or IA0? So how to calculate? One is the voltage and all the impedances are in series. So it's a series circuit. So if I simplify this circuit, I'll get like this. This is 1 and this is positive sequence impedance, negative sequence, let me put a reactor symbol, and zero sequence impedance, and then finally the fault impedance. 3 into Z fault, this is positive sequence, this is negative sequence, and this is zero sequence. This current is IA0, which is equal to IA1, which is equal to IA2. So how to get the current in this? So simply IA1 equal to IA2 equal to IA0 equal to 1.0 divided by J 0.22 plus J 0.22 plus J 0.34 plus J 0.3. So this calculation I have to do. Once I do this calculation, I'll get all the three components. Then how to get IABC? IA, IB, IC will be nothing but your A matrix multiplied by IA0, IA1, IA2. So once I get these three are equal because it's a series circuit. So once I get this value, I can substitute here, then I can substitute A and I can find the IABC. So let me switch over to my MATLAB interface and I'll show you that calculation how to do. Okay, so now I am calculating case 1, that is, or case 2, that is LL fault. So IA0 equal to 1.0 divided by J 0.22, or I have to give 0.22I plus 0.22I plus 0.34I plus 0.3I. So this will give me IA0. So IA1 equal to IA0, IA2 equal to IA0. So all three currents are equal. Then IA012 equal to IA0, IA1, IA2. And once I have this, then what I can do is define the A matrix. So let me copy the code from the previous lecture. So IABC is nothing but A matrix multiplied by IA012. So now I want to calculate up angle of IABC into 180 by pi. So that's it. So when I execute this code, so I am getting the final solution like this. Okay. So on the right you can see the A phase current is minus 2.77, B phase current is 0 and C phase current is 0. So this is the final solution. So let me just copy this to my previous code. From this, so this is from code. So this here apparently IA0 is nothing but minus J 0.92593, and from that if I calculate this, then IA is minus J 2.7778 per unit and IB equal to IC equal to 0. So of course because there is a line to ground fault, there is no current in the other two lines. A phase fault current is there, that is this one. Now what is the actual fault current? So IA is nothing but minus J 2.7778 into 5000. So this is in per unit and this is in amperes. So I'll get how much? Minus 2.7778 into 5000. So 13,889 amperes. And the angle is minus 90 degrees, just to show that it is lagging by 90 degrees, because we are assuming that the fault is purely inductive. Okay, so we concluded the case 1. So any doubts up to here? What I have done, I have taken the LG fault at bus 3, just copied the sequence network for the LG fault. From the sequence networks, I put the values in it, and from the values, I calculated the currents. So that is the same procedure we follow for other cases also. Any doubts up to here? Sorry, case 2 is over. Now let's take up the case 3, that is line to line fault. At bus 3. So if there is a line to line fault at bus 3, what I should do, I simply go to my previous notes, copy the circuit for line to line fault. So let me copy the circuit. So this is the circuit for line to line fault as we had noted before. So in this we can enter the values. So what are the values? So I know that this is 1 per unit. Voltage generated is 1 per unit. Z1 is J0.22. Z2 is also J0.22. And Zn, or this is Z0. The Z0 is J0.34. But this value is not useful now, because IA0 is nothing but anyway 0. So we are interested in what is finding out what is the value of IA1. So what is the Z fault? J 0.1 given in the question. So what is the total impedance? 0.22 plus 0.22 plus 0.1. So simply IA1 is 1.0 divided by j.22 plus j.22 plus j.1. So how much is it? So let me just use the calculator. 1 divided by, so I'll write it here. I'm just using the calculator. In fact, I'll show you. This is, sorry, I think this is LG fault. This is LL fault. So in this case, IA0 is anyway 0. IA1 is nothing but 1.0 divided by 0.22I plus 0.22I plus 0.1I. IA2 is nothing but minus all these three values. Then the rest of the procedure is same. I just copy and paste it, these three codes. So IA0, IA1, IA2 I am combining into this matrix. Then I multiply with A matrix to get the ABC and then like this. So let me run this code. So finally this is the solution I am getting. So these are the currents, IABC currents. So let me take the solution. Therefore, IA1 equal to minus J 1.85, IA2 is nothing but plus J 1.85 and IA equal to 0, IB is nothing but minus 3.2 per unit plus J 0, I am not mentioning that. So IC is plus 3.2 per unit. So in other words, IB is, I think I'll mention the 3.2 angle 180 degrees and IC is 3.2 angle 0 degrees. Now if I multiply with 5000, I'll get IB equal to 5000 into 3.2. So why I am multiplying with 5000 is from per unit I am converting into actual current. So that will be 16,000 amperes. 180 degrees and then IC is 16,000 amperes at 0 degrees. So fault currents is flowing only in B and C lines because it is line to line fault and IA is 0 amperes. So this is case 4. So what I did is very simple. I looked at the example and then I have just pasted that case. Now what is the next case? So IA1 is this, IA2 is this, and then finally I got 16,000 amperes for this. Okay, so I think case 4 is left now. That is line to ground fault at bus 4, at bus 3. So how to solve this? So again the procedure is simple. Just go to the previous nodes, copy the network here. So I go to my nodes and then LLG fault, I copy the sequence network. Network for LLG fault. So let me put the values here. So what are the values? 3 into Z fault is 3 into J 0.1, that is J 0.3. Neutral impedance is J 0.4. And what is the Z2, that is J 0.22, and this is J 0.22, and finally this is 1.0. So from this, can I find what is IA1, IA0 and IA2? So of course I can find that. So first let me find the total impedance. What is the total impedance? J 0.22 plus J 0.22 parallel with this. So what is the total here? 0.04 and zero point 0.3. So this is 0.34. These two are in parallel. So that is nothing but J 0.22 plus J 0.22 into J 0.34 by J 0.22 plus J 0.34. So let me use my calculator again. Case 4 is LLG fault. So in LLG fault, what I am doing? First ZT, total impedance I am finding, that is 0.22I plus 0.22I into 0.22I plus 0.34I. So I hope it is correct. So once I get the total impedance, I'll get the IA1. IA1 current will be total impedance, 0.1, 1.0 voltage divided by the Z total. And then I'll get IA2. IA2 I'll get by current division. So let me show how to get IA2 by current division. So if I go back to my notes, IA1 into, so look at this current division principle. How to get IA2 from IA1? IA2 is nothing but IA1 into opposite impedance, that is 0.34 by total impedance. J 0.34 by total impedance, J 0.22 plus J 0.34. So like this I have to do. Similarly, IA0 also I can get it. That is IA1 into J 0.22 divided by J 0.22 plus J 0.34. This is a simple current division principle. And once I get IA1, so this is 1.0 by ZT. Once I get these three component currents, then I can find what is my uh, IABC by simply multiplying with this. That's it. So let's do that. So I'm going back to my code. 0.34I divided by 0.22I plus 0.34I. Now IA0 is same except in the numerator I'll get 0.22. So once I get all these three currents, then I can find the rest of the three steps are exactly same. So this is the final answer I am getting. So let me copy the final answer. IA, IB, IC 5.65 angle minus 90 degrees is IA current. 1.5 per unit, 129 degrees is IB current, and then 1.5 per unit and 50 degrees is the IC current. Now if you multiply by 5000, this is in per unit, then you will get 5.65 into 5000. So that is 28,250 amperes. Very, very huge current. So from this, what you understand is line to ground fault is very severe. So 1.5 means 7,500 amperes, 129 degrees, and then this is also 7,500 amperes in 50 degrees. So this is a huge current that we are getting, 28,250. So even the last case also we covered. So let me just summarize the answers. Summary of answers. So EA equal to 1 per unit, Z fault equal to 0.1 J, neutral impedance is 0.04, and positive sequence is 0.22, and negative sequence is also 0.22. So for this particular data, what I got, fault and IA, IB, IC. So fault is triple line, balanced fault, then line to ground fault, line to line fault, and then line to ground fault. So how much current did I get in each case? So let me refer to my notes. 28,250 amperes, 7,000, draw the line also. 7,500 amperes, 7,500 amperes. For the line to line fault, this was 0, and let me just check before. Yeah. So I got 16,000 amperes, huge current, 16,000 amperes for this. For line to ground fault, what did I get? The answer which I got for line to ground fault was 13,889 amperes, and the other two were 0 amperes. And for the line to line fault, what was the answer I got? Let me refer to my notes. 21 amperes. 22,721 amperes. 22,721 amperes. So these are the final summary. So what you notice is magnitude wise this is more, but the other two are less. But in the case of triple line fault, all the three phases having 22,721 amperes, huge current. So what is the purpose of doing all these calculations? You know what is the fault current, you can expect this much fault current is going to come in the network. So based on that you can design the relays, you can design the circuit breakers, how much relay setting for fault current, all that things you can manage. How to limit the fault current? So by increasing this, by increasing the neutral impedance, I can limit the fault current. So if I want to limit this current to only 15,000 amperes, what should be the Zn? You can do that reverse calculation also. So anyway, since the time is up, this is the conclusion of the unbalanced fault calculations. I have taken an example, I solved all cases. So again, I request you to check the textbooks, take up some problems and solve. Another short announcement I'd like to make. Actually, next week on both days I am not available because I am visiting Delhi for India Smart Grid Week. So I might record my lectures and share that with you. So you can use that as this one. I will not be able to take the class on next Tuesday and Thursday because both days I am busy with the India Smart Grid Week conference. Anyway, so if you have any doubts, feel free to email me or feel free to ask now. I'll be online for a couple of minutes. So if any doubts, please ask. Summary which I had created. So for a triple line fault, For a triple line fault, this was the fault current. For line to ground fault, this was the fault current. For line to line fault, this was the fault currents, and finally like this. So this is what our final output of our calculations today.